Alrighty guys, so in today's lecture we are going to be learning about something called solutions. Now I know that in normal life we think about solutions as like the answer to a problem, like on a homework assignment or something like that. But in chemistry, a solution is defined as a homogeneous mixture of two or more substances. Now this part right here is easy to understand, mixture of two or more substances. It means that, it's a mixture, it's mixed with two or more things. This term homogeneous is a fancy way of saying that everything inside of the mixture kind of looks the same. The technical term is that it looks uniform. So like uniform, the uniform that you wear to school, everybody kind of looks the same because they're dressed the same. So in a solution, a homogeneous mixture, even though you combine multiple things in there, everything looks kind of the same. It looks uniform throughout. The opposite of a homogeneous mixture is a heterogeneous mixture. And in a heterogeneous mixture, it doesn't look uniform. You could see the different parts of the mixture, the things that combine in there. So I have a graphic here just to help you guys visualize it. So if we have, let's say, like a cappuccino or like a coffee or something, you know that it's mixed with a bunch of things. You have the regular black coffee, you got some milk, and you have some sugar. Now, in a homogeneous mixture, you can see that everything is blended together, right? You can't really tell the different components that are in there. But let's say you don't mix it very well together. Then you would have a heterogeneous mixture. You can see the lumps of milk and the sugar, and so this would not be a solution. So a solution is a homogeneous mixture. So this would be a solution, okay? Because you can't really tell the different components in there, right? If you look at this, I guess if you saw it in real life, you wouldn't be able to tell where the milk is or where the sugar is because everything is blended together well. So it'd be homogeneous. It looks uniform. But a heterogeneous mixture is not a solution because not everything is looks the same. You can see the distinct parts. Now, it doesn't just because you have a heterogeneous mixture doesn't mean that you didn't do a good job mixing it, right? Some other examples of a heterogeneous mixture would be like a chocolate chip cookie, right? That's a long word to write. A chocolate chip cookie. Um, Even though everything is mixed well, everything is combined, you can still see where the chocolate chips are. It's not like it's a mistake. Sometimes heterogeneous mixtures are not, it's not caused by a failure to mix it all together. That's just how it is. Or like maybe a pizza. A pizza is a heterogeneous mixture because you're mixing all these different ingredients together, but you can see the different components of that mixture. But in a homogeneous mixture, you can't see the distinct parts that made up that mixture. Okay? So that's just the difference between homogeneous and heterogeneous mixtures. But for this unit, we're going to be talking about homogeneous mixtures, specifically solutions. Now, solutions are made up of solutes and solvents. Easy way to think about it, a solute is the thing that's being dissolved, the thing basically that you have less of. And a solvent is the thing that's doing the dissolving, basically the thing that you have the most of. So going back to the coffee example, if our solution is coffee, okay, the coffee that we were talking about was made out of coffee. It was also made out of sugar, and it was also made with milk. I guess let's be a little more specific. Not instead of coffee, we'll put like a cappuccino. Okay, I'll just write cap. So a cappuccino is made out of coffee, sugar, and milk. Now, what do you have most of? You mostly have coffee, right? Most of the cappuccino is made out of coffee. So the coffee would be the solvent. Okay? You have some sugar and you have milk in there, but you don't have as much sugar as you do the coffee, and you don't have as much milk as the coffee. Since you have less of these are called solutes. So basically, these two things are getting mixed into the coffee. So these would be the solutes, and this would be the solvent. Okay? Easy way to think about it. Okay, another example of this would be like if you had lemonade, right? Lemonade is a solution because everything kind of looks the same inside of there. We know that lemonade is made out of water. It's made out of sugar. It's also made of some lemon juice, right? Okay, so which one would be the solvent, the thing that you have the most of? Okay, hopefully you said that it's water, right? The water would be the solvent because in lemonade you mostly have water in there. Whereas the sugar and the lemon juice, you have some in there, but not as much as the water. It's mixed into the water. So this would be the solute. Okay, so that's basically the parts of a solution. So when I talk about solute or solvent. I'm talking about what you have more of, what you're dissolving in there. That's just a terminology. Now, there's different types of solutions. Usually we think about, hey, we're mixing solids into liquids, right? We're mixing salt into water, but there's different types of solutions. So there are liquid-liquid solutions. An example of that would be vinegar. Vinegar is mostly water, right? This is the part that you have most of. The solvent is what you have most of. It's mostly water, but you have this chemical in there, the solute. This is called acetic acid. So basically, vinegar is just acetic acid mixed into water, just dissolved into water. Example of another type of solution would be a a liquid gas. Example would be carbonated or like sparkling water, where you have carbon dioxide dissolved inside of water. So you can dissolve gases inside of water. Another solution type would be gas. The air around us is a solution because if you kind of look, you can't really see. Sorry, I'm looking around at the air around me, but I can't really see like the different parts of the air, right? Everything kind of looks the same. I can't really see the air, but you get my point. So most of the air around us is made out of N2. This is nitrogen gas. I think about 70% of the air around us is nitrogen gas. But the other 30% are these other chemicals, O2, oxygen gas, argon, carbon dioxide, water vapor, and there's more. But the point is that it's mostly nitrogen gas, and that these other gases are dissolved inside of the nitrogen gas. So this is a mixture, a solution. The last type we're going to talk about are solid solids, where you have two solids that are mixed together. Usually you do this by melting them first and then combining them. And a good example would be steel. If you look at a piece of steel, I'm sure you can see like a piece of stainless steel somewhere around you. That thing it kind of looks the same throughout. It looks like the same type of material, but steel is actually made of carbon and iron. It's mostly iron, but what happened was we dissolved the carbon inside of the iron, and now everything looks the same. So just remember that solutions aren't just mixing or dissolving solids into liquids. There are all these types of solutions, and we'll talk about those later. Okay? All right. So why are we talking about solutions? When we talk about solutions, we have to what we usually try to figure out is the concentration. Now, concentration, we usually think about that as like focusing or making sure you're paying attention. But in chemistry, concentration is the amount of substance in a defined space. Another way of thinking about that is basically how much. How much of something do you have in the solution? Okay, so the concentration is how much of something you have in a solution. So if you have a higher concentration, that means you have more stuff inside that solution. But if you have a low concentration, you have less stuff inside of that solution. So we're going to take a look at some nutrition facts for my two favorite sodas, Sprite and Coke, to just see the different types of concentration we can talk about, or different ways we can talk about concentration. So let's take a look at this. We're trying to figure out which drink has a higher sugar concentration. Now, the serving size is the same here, and we're going to assume that one can it's the same size can. Okay? Now, which soda has a higher sugar concentration? Okay, so we're going to look for sugars, and you're going to say, hey, Sprite has 38 grams of sugar, and Coke has 39 grams. So since Coke has more sugar inside the one can, it has a higher concentration of sugar. Okay, but if we talk about a different type of concentration, we're talking about sodium, salt. We're going to notice Sprite has 65 milligrams of sodium. Coke has 45 milligrams of sodium. So you're going to notice that there's more salt inside the one can of Sprite than there is in the Coke. So even though Coke has a higher sugar concentration, Sprite has a higher sodium concentration because it has more sodium, more salt inside the one can than Coke does. Okay, and that's the gist of concentration. Concentration is just how much of something you have inside of a given space. Now, since this is chemistry, we are going to be doing everybody's favorite thing with concentration. We're going to be doing math. Okay, everybody loves math. So for concentration, we're only going to be talking about two types of concentration. We're going to be talking about molarity and molality. Okay, so the symbol for molarity is capital M. And basically, on the top, to calculate this, you just need to put the moles of the solute, the thing that you're dissolving, on top of the liters of the solution, basically how big the solution is. And then for molality, it's symbolized by a lowercase m, and then on the top we put moles, but this time instead of liters on the bottom, we have kilograms on the bottom. Okay, so the important thing to remember is that on the bottom of these fractions, you have to have either liters or you have to have kilograms. So let's say that in the problem you get milliliters or gallons. You have to turn it into liters before you can put it on the bottom of the fraction. Similarly, if you get like grams or you get pounds, you have to change it to kilograms before you put it on the bottom of the fraction. Same thing with the moles. You have to make sure moles is on top. But we'll get to that in a second. Okay, so let's do a few examples. So in this problem, it's asking us what is the molarity. So that means automatically, before even reading the rest of the problem, I know I'm using this formula right here, moles over liters, because I'm looking for molarity. And specifically, I'm going to be looking for capital M, which means that I need to plug in the moles and I need to plug in the liters. Okay, so let's read the rest of the problem. It says, what is the molarity of a 4.25 liter solution? So automatically I know, hey, this solution is 4.25 liters. So I'll put that on the bottom because I want liters on the bottom. Okay, that contains 5 moles of AgCl2. Okay, perfect. I'm dissolving 5 moles of AgCl2. So I'm looking for moles on the top. So I'm going to put 5 moles on the top. And then we're good to go. So we have 5 moles on top, 4.25 liters on the bottom. So if I want to solve this problem out, you always do top divided by bottom. So 5 divided by 4.25. And that'll give you 1.176. So my final answer for this problem will be 1.176. It's asking us for molarity. Since we're looking for molarity, the unit of measurement has to be capital M, molarity. So my answer, 1.176 molarity is my final answer. Okay, pretty easy. All you have to do for these problems is just plug and chug into the calculator. Now, it's going to get a little bit trickier than that, but that's a good introduction into the problem. So let's move on to the next problem right here. It's asking us, what is the molarity of a 5.8 liter solution that contains 100 grams of KBr? So it's asking us here to find molarity, right? We're looking for molarity. So that means I'm going to automatically know, hey, I'm going to be using this formula, capital M equals moles over liters. Okay? It tells us we have 5.8 liter, a 5.8 liter solution. So, hey, good for us. We can put 5.8 liters on the bottom. Okay, now we just need to find moles. The problem is when you read the rest of the problem, it says that we have 100 grams of KBr. Now, we cannot put 100 grams in here because we're not looking for grams on the top. We want moles on the top, so we can't do that. So instead, we are going to have to turn 100 grams of KBr into moles of KBr. Now, if you guys remember, the best way to do that is to set up a fraction. Everybody loves dimensional analysis, right? So I have grams of KBr. I don't want it. I need to turn that into moles. That way I can put it on the top of this fraction right here. So I want moles of KBr. Okay, I don't want grams, so I'm going to put grams on the bottom. That way they can cancel out. And so I have grams and moles on the same fraction. When you have grams and moles on the same fraction, you are going to always get the number from the molar mass, right? Because the molar mass basically tells you the grams that are inside 1 mole. Okay, that's what molar mass tells you. So what we're going to do is we're going to go on our periodic table. I know I don't have it on the screen, but make sure you guys pull it up on the side somewhere. And we're going to look for KBr. Now, KBr is made out of 1 K, 1 potassium, and 1 Br. So if you look at the number on the bottom of the box for potassium, you're going to see that potassium has a molar mass of 39.1. And that's going to be grams per mole. Br, on the other hand, bromine, has a molar mass of 79.9 grams per mole. And again, if you don't know where I got these numbers, you just look for these elements on the periodic table, and it's the number on the bottom of the box. So 39.1 and 79.9. So if I want to find the molar mass for KBr, I just need to add them together. Okay, so KBr is 39.1 plus 79.9. and that should give you 119 grams per mole. And just to make sure I got the right answer, since I did that one in my head, we're going to do 39.1 plus 79.9. That'll give you 119. So KBr has a molar mass of 119 grams per mole, and we've been doing this for a while, so you guys know that this means that it's 119 grams equals 1 mole. And this is what we're going to plug in to our fraction, this right here. Okay? So on our fraction, you're going to notice that we have grams on the bottom. I have 119 next to grams, so I'm going to put 119 right here on the bottom. And on the top, I have 1, so I'm going to put 1 on the top. So luckily for us, the grams of KBr will cancel out. And so now we just need to solve this out in our calculator. So our starting number is 100. We multiply the tops, but since it's 1, we can skip that. We're going to divide the bottom, so divide it by 119. And that'll give us a final answer, for this part at least, of 0.84 moles of KBr, because that's what we have left over right here. And so what we're going to do is we're going to take this number and put it on the top of this fraction. So 0.84 moles of KBr. And then now we can finally solve the last part of this problem by doing top divided by bottom, 0.84 divided by 5.8. And that will give you a final answer of 0.14. And I'm going to round that up to 5.145 moles of KBr. Okay? So there you go. That's how you would solve it out if you had moles instead of, or if you started with grams instead of moles. Okay? All you need to do is just work with the numbers that you have and change them into the units that you want. If you start with grams, you're going to turn it into moles. If you start with milliliters, you'll turn that into liters. Okay? So let's move on to the last problem we're going to do together, and then we'll be all done for today. Okay, so here we have, what is the molarity of a 750 milliliter solution that contains 8 grams of NaCl? Now, if you think you could try this on your own, feel free to pause the video and do so, but if not, that's okay. I'm going to go over it step by step. Okay, so let's go over this problem. So since we start with molarity, I'm going to use the formula capital M equals moles over liters. The problem is we don't have moles or liters, right? We have 750 milliliters and we have 8 grams of NaCl, which means I cannot put in any of the numbers into this fraction. I have to change them first. Okay, so let's start with the one that we just learned how to do. We learned how to do the grams to moles, or we reviewed it because you guys learned this a long time ago. So we have 8 grams of NaCl. We want to turn that into moles. So I'm going to set up a fraction. On the top, I'm going to put moles of NaCl. And on the bottom, I'm going to put grams of NaCl. That way they can cancel out. Now, if you go on your periodic table, since you have grams and moles, you want to turn this into molar mass. So molar mass. And so the molar mass of just Na, if you look on your periodic table, is 23 grams per mole. If you look at Cl chlorine is just 35.45 grams per mole. So if I wanted to find the molar mass of NaCl together, I would have to just add them up. So I'm going to go on my calculator. Oh no. You're going to go on your calculator, and then you're just going to add them up. 23 plus 35.45. That'll give you 58.45. So that means NaCl is 58.45 grams per mole, and we're going to plug that into our fraction. So the number next to grams is 58.45, and the number next to moles is 1 because it's per mole. And so what we're going to do is just cancel out the grams of NaCl, and then we can punch it into our calculator. Our starting number is 8. We can ignore the times 1, divide it by the number on the bottom, 58.45, and that'll give us 0.13, and I'm going to round it up to 7. So 0.137 moles of NaCl. Okay? So on the top of our fraction, we're going to put 0.137 moles of NaCl. And then on the bottom, we have to put in liters, but we don't have liters, we have milliliters. So what we're going to have to do is we're going to have to take the 750 milliliters and we have to turn that into liters. Now, we're going to have to use a conversion factor, and this is going to be written on your assignment, so it's okay that we don't have it right here. So just make sure you guys are looking at your assignment carefully to find the conversion factor. On your assignment, you will see this equation right here. It's going to say 1 liter is equal to 1,000 milliliters. So what we're going to do is we're going to start with 750 milliliters. We're going to set up a fraction. I don't want milliliters. I want liters. So I'm going to put milliliters on the bottom, and I'm going to put liters on the top. We're going to use this fraction right here. What number is next to liters? Number 1. So we're going to put in 1 right here. What number is next to milliliters? 1,000. So we'll put 1,000 on the bottom. Milliliters cancels out, and then you'll get liters. So we just need to chug this into our calculator. 750 divided by 1,000, and that'll give you 0.75. So 750 milliliters is the same thing as 0.75 liters. We're going to put that on the bottom of our fraction, 0.75 liters, and there you go. We can solve this out now. So all we got to do now is go on our calculator, top divided by bottom, so 0.137 divided by 0.75, and that'll give you a final answer of 0.183 capital M molarity. Okay, so what does all of this mean? We've been doing all these calculations, but what does it mean in real life? So basically what this is telling us is that, hey, let's say I have this container right here. Okay, inside of this container, we have a 750 milliliter solution. So the volume of this container, the stuff in this container, is 750 milliliters. And it contains 8 grams of NaCl. So I have 8 grams of NaCl, right? So I'm going to just draw NaCl. NaCl is just salt. Okay, so inside of this container, we have 8 grams of NaCl. So if I have 8 grams of salt dissolved inside of a 750 milliliter solution, the concentration, basically how much stuff there is in there, how concentrated it is, it's going to have a concentration of 0.183 molarity. That's basically all this is talking about. Molarity concentration is a way for us to tell other people and let even ourselves know how much salt is in here relative to the size of this container, right? And this isn't going to change if we change containers, right? If I took some of the the salt water in here, let's say I took this much of the salt water and put it into a different container, like a smaller container. Okay? Even if I put it into a smaller container, this is still going to be the same concentration, right? Because you're changing how much solution there is. Let's say this is just 200 milliliters. And obviously, there's not 8 grams of salt in here, right? Because we only took part of it. But the concentration will stay the same. It's still the same concentration. So this is very helpful when we do labs because we can make a lot of a chemical, a solution, and we're still able to use it in different ways while keeping the same strength of the solution, the same concentration. Okay, so hopefully that was helpful. This is what we're going to be doing in your assignment today. Let me know if you guys have any questions, and good luck on your assignment, everyone.